Well, one of the small advantages of being chair of this program committee is that I'm able to strongly influence the choice of plenary lecturers. And I felt that being in Italy and given the recent nature of the trial of the people from L'Aquila, of the scientists associated with the L'Aquila earthquake, that we would all be interested in hearing some of the problems associated with public advice given by scientists and how it can be misinterpreted. So I'm very pleased today to call on Professor Paolo Gasparini from the University of Naples. He was not one of the defendants at the L'Aquila trial, but he acted as a consultant for the defense, and he's also been heavily involved with several projects aimed at improving prediction of earthquakes. So without further ado, I asked Professor Gasparini to come and deliver his talk, which is entitled Natural Hazards and Scientific Advice, Intersections Between Scientists, Decision Makers and the Public.
Thank you for your introduction and for the presentation and for the invitation. I must say that was quite reluctant at the beginning to accept the invitation because the subject is not easy and also is very, let's say, personal opinion play a strong role in it. I've tried to be as more honest as possible in the presentation. And anyway, I've been helped by many people in it. I want to acknowledge their help just from the start. They are Mauro Dolce from the Department of Civil Protection, Warner Marzocchi and Giulio Servaggi from INGV, and the ideas that I put forward are the result of many discussions and had with Tom Jordan from SCEC, Gaetano Manfredi from the University of Napoli, Franco Barberi, University of Rome, Gordon Wu from RMS, Friedemann Wenzel from KIT, and Jochen Schau from GFZ. So they are all, in a way, share a co-authorship in a way with them. Well, the outline of the talk will be the following. First, let's investigate why losses due to natural hazard are increasing. That's questions that have been often asked by the public, by the administrators also. Then the role of scientists and decision makers. Recent examples of false or missed alarms. What I want to stress out is that there are many examples of good, let's say, management of emergency situation, but there are also many examples of false or missed alarms because, well, we will see why in a while. Then we will focus on the extreme case, the L'Aquila 2009 earthquake affair. We'll have a more in-depth consideration on it. Then the problem of dealing with very low probabilities and possible scenarios of interaction. Why losses due to natural hazard are increasing? This is a very popular plot made by Munich Re, showing that the number of events in the last 6 years have been in total increasing, but because the event related to climate change, let's say not geological event, but an event related to meteorology, hydrology, and so on, they have been increasing. In red, you see the events, the geological event, geophysical events, earthquake, tsunami, and eruption, they have been more or less constant. The number of them have been more or less constant in the last 60 years. Anyway, the number of the losses due to natural event have been increasing, mainly in the last 20 years, 20, 30 years. This is partly due to the increase of events related to meteorological events, but partly, or a great part of it, is due to increase of vulnerability of the human system. Why there is this increase of vulnerability? Because an increasing number of people is concentrating in urban areas. This is a very famous plot from the United Nations, published in 2004, that shows the increase of population and, until now, and the expected increase of population until 230, and the distribution of population between cities, urban areas, and countries. In 2006, 2007, the total number of people living in urban areas has become more than the people living in the countries. And this difference is, this increase is sensitive not only in industrialized countries, but also in less developed countries. Now we can expect that in 2030, about 82% of the population of the industrial countries and 57% of the population of less developed countries will be living in urban areas. These plots indicates the influence of the different parameters defining risk. So the hazard is in yellow, in vulnerability in red, and exposure in blue in different cities of the world. The size of the circle concerning the cities is proportional to the risk index of that given city. You see immediately in this picture that the red color is dominant. It means that vulnerability is the dominant factor in increasing the losses due to natural effects. This means that also events which are mild, are not very high, and in the past have not produced great damage. Now they produce great damage. Some samples are reported here. The Virginia earthquake of August 23, 2011 made some significant damages also in Washington, D.C. that was 135 kilometers away. The magnitude of the earthquake was 5.8, so the event was quite mild. The Emilia earthquake in Italy of May 2012, magnitude 5.8 again, made casualties and extended damages. The Christchurch earthquake of February 22, 2011, magnitude 6.3, so not extreme event, made several hundreds casualties and a lot of damages. Then we have that the so-called black swans, so extremely rare events with huge impact on human life, structures, and socioeconomy, which in the centuries before happened often in areas where they were practically not inhabited, now occur frequently in areas which are inhabited. And so a great increase of damage is also due to this black swans event. So, what is the role of scientists and decision makers? Well, first of all, we have to say that in this situation, communication is a major challenge for the management of risk nowadays and even more in the future. We live in an exponential growth time. World population is growing exponentially. Cities and megacities are exponentially increasing in complexities. Cities are becoming risk attractors because of their increase of vulnerability. That's very important, not increase of hazard, but just vulnerability. Communication of scientific information is a complex and still unresolved task fundamental to prevent cities to become natural traps. Now, scientific advice for natural hazard management is mainly asked for urban and land use planning and for emergency management. Urban and land use planning imply advice in long-term hazard and risk assessment. Long-term means tens of years, of hundreds or several tens of years. Emergency management imply short-term hazard and risk assessment. Short-term means weeks, days, sometimes hours. So the tasks are completely different because scientific advice for urban and land use planning is a demanding, complex, but not complicated task because there are no urgency requirements. We have as time as we like to give an answer to question, and the responsibilities are generally fairly well defined. Scientists give a scientific advice, and the politicians make political decisions. Main requirements of scientific advice are careful consideration of all possible hazards for a given area, harmonization and probabilistic quantitative evaluation of the parameters defining hazard occurrence. This is being done and has been done in a number of cases, and the only problem concerning the first point, the careful definition of hazard, is that also interaction between different hazards must be considered, both for cascading domino hazard, for instance, earthquakes producing tsunamis or landslides or other earthquakes and so on. And also combination of hazards must be considered. Two different hazards can occur. It's quite rare, but they may occur at the same time and have an enhanced. And the second one, we will have an enhanced effect on the system that we are trying to protect. A good example of harmonization, comparability of risks, and of different risks threatening a single city has been made for the city of Köln in Germany, where during the last 10 years there have been a lot of work, a lot of research trying to harmonize the parameters defining the hazards and risks in the cities, and having a comparable estimate of the annual probability of occurrence that you see on the vertical axis, and on the horizontal axis is the losses in millions of euros. So the decision, the one making decision in the case of Köln must decide, for instance, to invest more money either for frequently occurring hazards like storms or floods, which produce anyway a minor losses, or for longer return period events like earthquake, which produce much higher losses once they occur. Of course, I've said either or, it's not a either or. I mean, the resources can be modulated in a way to account for, to try to mitigate both kind of effects. The scientific advice for an impending emergency situation is dramatically different. There is need of rapid response. Rapid response may be of the order of days, but in many cases of hours. There is no clear separation of responsibilities between scientists and decision-making. There are no established rules for information to the public. Nowhere exists a established rule to inform the public, with the possible exception of Japan. No established protocols for real-time risk mitigations actions. So this figure shows really what is the challenge. The scientist should articulate a lot of information, many times contradicting information, the differences of opinion, large uncertainties, in information useful for public officials, which must just has the possibility of a yes or not, so a Boolean logic decision. And the real challenge is this one. Public officials must have the information apt to give them the possibility of saying yes or not to a given action, and scientists must strive for giving a kind of information which can be easily used for this. This is the real problems. Now, in an idealistic world, the role of scientists as decision makers should be more or less this one. Scientists are responsible for hazard and risk assessment and give the information to emergency managers. Both are responsible of education of the public, but emergency managers are responsible for decision making. So the decision making should be at emergency managers. The decision making must take into account the human behavior response of the population on risk, and the final aim of all this chain should be to make possible for individual decision making. So to have a kind of education to the public and the kind of formation for which, in an established framework, single individuals can take their own decisions. Like we will see, like is usually done for terrorist attack or for pandemic diseases. Now, this ideal division of tasks and responsibilities is not usually respected in emergency management. While providing assessment of risk, scientists often suggest more or less explicitly risk mitigation actions and are asked to contribute to inform the public. Scientific advice is rarely given in quantitative probabilistic terms, so it's difficult to use. Emergency time is different for each kind of hazard. Successful results have been obtained in many cases for the kind of hazards we have a longer preparation or a longer duration. For instance, we have very good successful results in management of Mount Soufriere of Montserrat eruption in the 90s, Mount Pinatubo eruption, and for the floods which occurred in Central Europe, for instance, in the recent years, and sometimes also for hurricanes. Earthquakes are an extreme case of decision-making because in this case, decision must always be taken, let's say, in less than 1 day, in very short time. And the uncertainty underlying the decision is much higher than in the other kind of hazards. So I will concentrate now the rest of the talk more on earthquakes because also because the conclusion that we can reach regarding earthquakes may be applied also to other risks. Now, as I said, there are examples of risk which have been with emergency, which have been well managed, but there are several examples of false or missed alarms that have been issued for different kind of hazard. I just mentioned cases occurred in last four or 5 years. For instance, in case of two hurricanes, the Irene's hurricane and Sandy hurricane, the 370,000 New York citizens were evacuated under the threat of these two hurricanes. For both was a false alarm because the power of the hurricanes decreased very much when they hit land. And so there was many private companies and industries threatened to undertake legal actions against Mayor Michael Bloomberg. In this case anyway, no large blame was on scientists, but just on the decision maker. Another debated case was were the actions taken to protect aircrafts during the explosive eruption of Eyjafjallajökull in Iceland in 2010. You will remember certainly it. Scientists provided a continuous simulation of ashes density in the plume and forecast of plume direction. The British Civil Aviation Authority established the threshold levels for the ash density. Several flights over Europe were forbidden, and some airports were closed for several days. The Civil Aviation Authority manager was severely blamed to have been too cautious, but there was no blame on scientists and no legal action, as in the former case also. Another case of missed alarm was the Madrid snowstorm of January 9 in 2009. 45,000 people were trapped at the airports, and 400 kilometers of vehicles were trapped on the highways because the authorities wanted to give warning until the false alarm probability was very low. And then they gave the warning too late to reach the people. In this case also there is much discussion, much blame from the media to the authorities, but no legal actions were made against anybody. An outstanding case of missed alarm was the magnitude 9 March 2011 Tohoku earthquake and tsunami that hit the Honshu coast on March 11. And this slide shows the probability map for 1 year, for the period 1 January, 31 January, it's a retrospective calculation, so it was made after the occurrence of the earthquake. But anyway, for this period, the probability, this map showed that there was an increase of probability of the occurrence of a large earthquake in the area, but as you can see in this other slide, the probability decay gain was about 100. The weekly probability of an earthquake of a magnitude 8.5 or greater was 0.12%, so very, very low. And to make decisions in this very low environment is very low case, probability is very difficult. In that case, there was the Japan Meteorological Agency is a very good earthquake early warning system. And you will see here that when the waves, the P waves, the blue line reach the first station, there is a early warning released to the people here. And the early warning was quite good for the people. You see the different area where it was released. But the early warning was not released for Tokyo because Tokyo was too distant and it was thought that it could not have been reached in a significant way by the waves. Because this causes a lot of blame from the Tokyo people. The government of Japan and the chief manager of the Japan Meteorological Agency admitted the inadequacy of their action and apologized and indicated TV broadcast. In this case, there were no direct legal action for the earthquake, but there was also one reason maybe for this, because all these disasters were overshadowed by the Fukushima nuclear plant disasters. that, and so the attention of the people, of the authorities, and everybody was deviated, was shifted to the nuclear disaster, and that was the real case. But anyway, also in this case, there were no legal action concerning the earthquake and the tsunami itself. The same occurred for the Christchurch earthquake in New Zealand. On September 3, 2010, there was a magnitude 7.1 earthquake in an area 40 kilometers away from the town of Christchurch, and there were no casualties. A few months later, on January 21, a magnitude 6.3 earthquake occurred just 5 kilometers away from Christchurch and hit the region, producing 180 casualties and 7,000 injured people. In this case, we have here a map of the situation. The green here was the epicenter of the first earthquake. Then the seismic activity shifted gradually in this direction toward Christchurch, and on January 21, the earthquake occurred on Christchurch. So there was a gradual shifting of seismic activity. Notwithstanding this, no alert was given during the aftershock sequence, and all some blame was on scientists and administration. There were no legal actions against them. The only legal action were against the designers and builders of some collapsed structures in Christchurch. Now we come to the L'Aquila case. What happened in L'Aquila? L'Aquila is a city lying in one of the highest seismic hazard zones of Italy. Here you see a map of seismic hazard in Italy, and here is an enlargement of the zone around L'Aquila. So this map says that acceleration of 0.25 to 75 G are expected with a return period of 475 years. It means with a 10% of exceedance probability in 50 years in that area. And these are the acceleration that are expected with that return period on the basement rock. It means that this map was public. This is known to all the managers of the area. It's known to all the emergency managers. It's known to the public. It's been always published in the website of Civil Protection and of INGV. In the L'Aquila region, there have been sequences of earthquake in the last 60 years, reaching magnitude as high as 4.7 without having a higher event after that. There were several of them, and in this 60 year, there have been 13 earthquakes with magnitude greater than 4, in this sequence. Then, on January 2009, another sequence started. You can see here in the plot, the upper plot here, in red, the cumulative number of earthquake for days, and the scale is here, and the magnitude of the earthquake, the magnitude scale is here. You can see that there were magnitude not higher than 4.1 before this sequence, then culminated with a shock of 6.3 on the day on April 6. If you look at the sequence before the April 6 event and compare it to what happened some years before, for instance, in 1985, here, you can see that the sequences are quite similar. This sequence did not result in any stronger event. This resulted in a stronger event. If we go to look at the origin of the earthquakes, you can see here the distribution of the epicenters of all the earthquakes of the sequence, and here is the location of this vertical section through the city of L'Aquila. Within this violet curve are the foci of the earthquakes which occurred before the main shock. And they were defining a structure, active structure in this direction. This is the event which occurred on April 6, and these are the aftershocks. You can see that clearly that the event of April 6 and the aftershock were on a structure which was very differently oriented in respect of the shocks occurring before. And this structure was oriented in a way that the beginning of nucleation occurred just below the town of the city of L'Aquila that was here. If the earthquake had occurred probably on the other structure, the situation would have been different. So there were no easily interpretable situation. Let's resume what happened in the L'Aquila affair sequence. Well, as I've said, seismic activity increased in January 2009 and continued in following months. During the period of the sequence, Mr. Paolo Giuliani, a technician of the National Institute of Nuclear Physics, issued prediction of impending large earthquakes in the region. One important thing is that the predictions were not backed by scientific institution. Scientific institution made an official statement that they were personal issues of Mr. Giuliani, but not of the Institute. These unofficial predictions were based on variation of radon concentration measured with gamma ray detectors. The used correlation procedures were not made available, and when presented to a commission that was appointed after the earthquake by the International Commission, appointed after the earthquake by National Civil Protection, this correlation resulted to not have a scientific basis. At least two of the specific predictions result to be false alarms, as admitted by Paolo Giuliani himself, but generated widespread public concerns. INGV and the Department of Civil Protection responds with statements about earthquake prediction, and on March 31, the seismology section of the High Risk Commission, a consultant body that helps Department of Civil Protection in Crisis Management, was convened in L'Aquila to give an opinion on Giuliani's prediction. Then, the following day, after the meeting, the mayor of L'Aquila, who participated to the meeting, asks for the state of emergency because the damage from swarm was estimated to be around 15 million euros, and the municipality plan had been activated, and several schools were evacuated after the felt event. Then, after two quakes of magnitude 3.9, 5 and 3.9 occurring a few hours before, a main shock of magnitude 6.3 occurred at 3:32 a.m. of April 6. The quake killed over 300 people, injured more than 1,700 persons, and destroyed or severely damaged about 20,000 buildings. Then, after almost 3 years, on October 22, The Court of L'Aquila condemned at the first level some of the participants of the March, at the March 31st meeting of the High Risk Commission. The verdict was that the seven scientists and public officials who attended the High Risk Commission meeting were found guilty for involuntary multiple manslaughter and multiple serious injuries. The faults consisted in negligence, incautiousness, and unskillfulness. They were condemned to 6 years in prison, perpetual interdiction from public offices and legal interdiction during enforcement of sentences, but the execution of these two issues was suspended until the final level of judgment, and to financial compensation to the families of the victim, about 8 million euros, with immediate execution. So this was not suspended, but was immediate. The verdict, motivation of the verdict was very long, about 940 pages, but can be summarized in a few lines. They say, okay, an high risk commission was convened in L'Aquila following the seismic sequence culminated with a magnitude 4.0, 3.9 the day before. All the 7 indicted people are considered members of the commission, but only 4 actually were members. The commission had peculiar duties of assessment of the risk situation in L'Aquila and correct information to the public. This is a very controversial point, because in the let's say in the decree of institution of the Great Risk Commission, this is not explicitly said. The Commission has failed those obligations of assessment and information, and all the High Risk Commission components are responsible for the violation of such obligation. The fault, as I say, consisted in approximate evaluation of the situation and in having contributed to spread reassuring messages to the population. Because of the reassuring messages, 29 dead people out of 309 fatalities that, according to the court, were used to run away from their homes when alarmed for earthquakes, remained in their homes on the night of April 6 and died as a result of the collapse of the buildings in which they had remained. Now, let's go back one moment to the 31 March meeting. The meeting was held with the participation of many local authorities, including the L'Aquila mayor. Experts were neither alarmistic nor reassuring, concluding that large earthquakes are not predictable deterministically. A large event in the short term is unlikely. L'Aquila is one of the areas in Italy with the highest seismic hazard. After the meeting, the Bernardinis and Barberi held a press conference reporting the above-mentioned conclusion. However, no audio recording of the conference is available. There was no press release. The minutes of the meeting were published after the earthquake. One additional point is that one of the civil protection officers, the Bernardinis, before the meeting, made a statement that he says that seismologists say that there is a release of energy by this earthquake, and this is a favorable condition. And this sentence is one of the main points used by the judge. Now, participants at the 34th meeting were some government officials of the civil protection, government-appointed scientists, so the true high-risk committee. The government officials of the civil protection were not part of the high-risk committee, and one scientist, Giulio Selvaggi, who was there just for providing data, but was not member of the committee. Again, the main faults, according to the sentence, was the High Risk Commission and some of its members in several interviews stated that the seismic sequence had to be considered normal, and that the probability of an impending higher M event was minor. This was explicitly said in the sentence. Then, the High-Risk Commission did not behave as an unitarian body because in the meeting only statements were produced without explanation of scientific basis. Hence, not all the members were aware of the reliability of the statements. The statements were what I've shown before, so I think this was ridiculous because all the data, the backgrounding this information, they were available to high-risk committee. They were in the website of INGV, for instance, and they were also in their own experience. And so, anyway, this is the way usually the consulting bodies behave. The verdict motivation indicates what a legitimate behavior should have been. The sentence says explicitly, it would be sufficient to not say sentences as, it is not possible to make prediction. Seismic prediction have no scientific base. The simple observation of several small earthquakes is not in itself a precursor. Some strong earthquakes have been preceded by small shocks. In many cases, small earthquakes have not been followed by strong events, and so on. In other words, obvious scientific data and conclusion should have been dismissed and hidden, according to the judge. Now, one point is why the high-risk commissioner, the scientists involved, say that it was a normal situation in a high-risk area. This is why, in majority of cases, seismic sequence are not followed by higher earthquakes, higher magnitude earthquakes. If we made an examination of all the earthquakes occurred in the period 1983 till 2009, and there were 698 seismic sequence or single shocks with magnitude between 3.5 and 5, and none of them was followed by a magnitude higher than 5.5 earthquakes within 20 days in the radius of 200 kilometers. According to Marzocchi and Zhuang, about 8 on 1,000 earthquakes of the larger time scale are not followed, by strong event. If we go again to make a retrospective analysis of the Aquila sequence, this has been made by the Warner Marzocchi and Tom Jordan. There was on April 5 at 8 a.m., one day before the earthquake, the probability of occurrence of a larger, of an earthquake larger than 4 was of the order of 0.01%. So it was 1 over 1,000. So the situation, I think we can claim that the situation was normal. The probability was very, very low. The following day, the probability, increased to 0.05% on 6 April at 1 a.m. It means 2 hours before the earthquake. So still the absolute probability had increased about 5 times, but were still very, very low. That's at the best of on our knowledge. Now, what is the impact on society of the L'Aquila sentence? Well, the impact was that from that moment, a number of cases occurred when every time you have an earthquake, you have, let's say, emergency actions to be taken. So occurred after a 2.8 magnitude earthquake into town, a seismic sequence. In Garfagnana, there were earthquake with a maximum magnitude of 3.2, and the mayor, following communication received from the Prime Minister's office, we suggest to leave your house and stay outside, said the population. So at least to 25,000 people stayed out of their houses overnight. Let's say we want to resume the consequence. There is one consequence was to increase a defensive attitude from emergency managers, and this means to give out the decision responsibility. One other consequence is general loss of credibility, because after a number of false alarms, people don't believe anymore to what you are going to say. Then one other very in my opinion, dangerous thing is the indiscriminate application of the precautionary principle that has been encouraged. Precautionary principle has, of course, many merits, but must be ruled. It cannot be applied without any rule. Applying it without any rule gives catastrophic consequence, because the precautionary principle in an absolute sense cannot operate. A given community must select a risk choice they want to accept. A demand for a technology to be put into operation without risk is a metaphysics desire. There is no human activity, there is no risk. We have to take risk, but risks must be balanced with calculation. An absolutistic use of precautionary principle will stop forms of scientific investigations and application of innovative techniques, even for protecting humanity. After the L'Aquila was how long time do I have still? 5 minutes, okay. After the earthquake, the Department of Civil Protection appointed an international committee for earthquake forecasting formed by 10 scientists from several countries, all experts of seismic earthquake risk. This commission should report on the current state of knowledge of short-term prediction and forecasting of tectonic earthquakes and indicate guidelines for utilization of possible forerunners of large earthquakes to drive civil protection action. The result of the works of the commission was a report on this. The finding and recommendation were released by DPC and endorsed by IASPEI, the International Association of Seismology and Physics of the Earth Interior, and finally published on the Annals of Geophysics. The main issues, the Commission introduced, in a way, the concept of operational earthquake forecasting. It says when we have to deal with very low probability hazard, while the probability gains can be high, larger than 100, the daily or weekly probabilities of large earthquakes typically remain low, less than 1% per day. So anyway, even in this situation, preparedness actions appropriate to such high-gain, low-probability situation could be implemented, but have not been systematically investigated anywhere in the world, not only in Italy. Standardization of operational earthquake forecasting procedures is in a nascent stage of development, And incremental benefit of this of operational earthquake forecasting for civil protection have not been still yet convincingly demonstrated. Under these circumstances, governmental agencies have been cautious in developing operational probability. Now, to develop an operational probability, you have to have a reference model. You have to say, I will assess probability in this way, and the reference model will be this one. There is an international group who is working on this and has developed a model based on the ETAS, Epidemic Type Aftershock Sequence. This model applied to clusters is mainly fit for aftershock, but has worked well also for foreshock, and embodies all the information that we have on the earthquake patterns. Now, this model will be integrated with other different models, so to have an ensemble forecasting model. Each model should be weighted according to its forecasting performance. This is made within one international experiment that called CSEP, and it includes groups from United States, Europe, Japan, Australia, and so on. Now, everyone of us knows that when there is an earthquake, we have continuously claim of people that say, we have seen that kind of parameter increasing, radon or electricity in the ionosphere or things like that, or electromagnetic change and so on. But this cannot be accepted in that way because a forecast validation must be made, and the ISEC criteria for operational fitness are to check the quality of the forecast, its reliability and seal, through retrospective and prospective testing, consistency among different forecasts across temporal and spatial scale, a need for integrated model development, and the value of the forecast to users. So this final model should embodies all the statistical models used for earthquake forecasting and also the forecasting, the single forecasting information. One resolved the problem of model. Let's say we have this the model at a final stage, very good model. Now the next model is when you say that there is a given probability. How can we evaluate the action that should be done? The yes or no of the slide that we have seen before. This must be done through a cost-benefit analysis. A very simple way to do it is that, let's suppose the cost of protection against loss L is C, and C is minor than L. If the short-term earthquake probability is P, the policy that minimizes the expected expense E is that you must protect, so take the protection action if P is greater than C divided L. Do not protect if P is minor of C, of cost divided loss. This kind, I have presented it in a very simple way, but of course it's not easy to calculate this value, because you have to calculate monetary valuation of life, valuation must account for information in absence of forecast, and so on. The important thing is that you have at the end a kind of curve like this. In black, you have the probability with, let's say, the financial losses due to unprotected earthquake, and in red, the one with protected earthquake. And using this kind of calculation, retrospective for L'Aquila case, it came out that assuming some reasonable factor for the cost-benefit analysis, all the evaluation made with above said principles were below these reasonable factors. So the suggestion should have been to take no action in the L'Aquila case. This doesn't mean that you shouldn't take actions in general. And the objective operational forecasting is just to identify which are the actions that should be taken at a given level of probability gain. Some of action are very simple. For instance, this is the Bay Bridge that was damaged during the Loma Prieta earthquake and produced many casualties. It came out that the Bay Bridge, this part that collapsed, had construction defects. And so an inspection of them would have prevented its collapse. We can, earthquake hazard is a low probability, high consequence international peril, like pandemic and terrorism. There are public pandemic and terrorism alerts which are advisory, not compulsory, and do not cause panic. Increase in seismic risk advisory may also be provided to the public, and the public can be nudged to make some action, not obliged. And so, in conclusion, I would say that the things to remember are that in all sciences there is always uncertainties, and under condition of uncertainties we have to take our decision. As all the philosophers already knew, for instance John Locke, we take our decision in the twilight of probability and not in the clear light of uncertainties. And the calculus of probability is essential to decide upon our conduct, said Blaise Pascal. Dealing with natural hazard, we deal with very low probabilities and high uncertainties. So uncertainties must always be established at its best. The concept of probability is not included in the legislation of many countries, including Italy. In Italy, there is no legislation on insurance for natural hazard. So modification of legislation is necessary to come out of cases like L'Aquila. The final aim should be for people being able to make decisions individually within a probabilistic framework. I think, of course, it is maybe a very distant goal, but and the data protocols must be transparent and readily available to the public. This can be made soon. It's not a distant goal. And reaching this goal will be an incommensurable but precious task.
Thank you very much, Paolo, for really a fascinating and very well-prepared talk. I don't think it's time for discussion because the sessions are about to start again, but I'm sure that Professor Gasparini will welcome informal questions afterwards for those of you that are interested. Thank you.
Thanks.